Hello, calculus fans. So up to this point, we've spent a lot of time computing integrals by finding antiderivatives and applying the fundamental theorem of calculus. We're going to find out, though, that sometimes we can't evaluate an integral exactly. And that's because a lot of times it's hard or even impossible to compute an antiderivative. And in fact, you don't really have to work very hard to find examples. All right, so as a couple of examples, here are two integrals that cannot be computed exactly because it is actually impossible to find antiderivatives. So when we talked about the integral, we defined it as a limit of a Riemann sum. This was something that happened right at the end of calculus 1. In order to evaluate the integral from a to b of f of x dx, we took the interval a to b and chopped it into n equal size subintervals, and they all have the same width delta x, which is equal to b minus a over n. Then what we did is we said that the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the sum where k goes from 1 to n of f of xk star delta x. And xk star is any point in the subinterval x sub k minus 1 to x sub k. We could, as an example, choose xk star to be the left endpoint of each subinterval. And in that case, we get that the integral from a to b of f of x dx is equal to L sub n. So this is the left endpoint approximation. And it's the sum where k goes from 1 to n of f of xk minus 1 delta x. So this is, as we said, it's the left-hand Riemann sum, or you could call it a left endpoint approximation. Let's take a look at a picture of a left-hand Riemann sum. So here's an example of some function on an interval from a to b. So I guess this is going to be a and this is going to be b. And on each subinterval, so this one has 4 subintervals. Here's the first subinterval. We choose the height of the rectangle to be the value of the function at the left endpoint. And we'll just add up the areas of all these rectangles, and that'll give us an estimate of the integral. And it's not going to be a terrible estimate. On the other hand, it's not going to be great either. On the other hand, we could choose xk star to be the right endpoint. And in that case, we would say that the integral from a to b of f of x dx is approximately equal to r sub n. And now it's the sum where k goes from 1 to n of f of xk times delta x. And similar to the left-hand Riemann sum, this one is called a right-hand Riemann sum, or you could call it a right endpoint approximation. Let's look at a picture of a right-hand Riemann sum. This is the same function that we had before, but now we're taking the sample points on each subinterval to be the right endpoint of each subinterval. And we get a different approximation. Might be better, might be worse. I don't know. This is just a specific example. And then finally, we could choose xk star to be the midpoint, which we'll call xk bar, of each subinterval. And if we do that, we get something called the midpoint rule. And the midpoint rule just says that the integral from a to b of f of x dx is approximately equal to m sub n. And this is the sum where k goes from 1 to n of f of xk bar delta x. And let's look at a picture to illustrate the midpoint rule. All right, once again, it's the same function, but now on each subinterval, we take the midpoint of the subinterval and go up to the curve to find a height for a rectangle. There's one other type of approximation that comes from taking the average of L sub n and R sub n. So if we take these and add them and divide by 2, we can simplify this expression. We'll combine these. Now we can simplify things by not writing this as sigma notation. And when everything gets combined, this is the expression that we get. So we get a delta x over 2 out in front, And then we have f of x naught plus 2f of x1 plus 2f of x2 and so on, up to 2f of xn minus 1 plus f of xn. So the coefficients on the first and the last term are 1, and all the other coefficients are 2. Now this is called the trapezoidal rule, and to illustrate that, here's a picture. So in the trapezoidal rule, we make trapezoids by going up to the curve on both the left and the right endpoints of each subinterval. And so the trapezoid rule in certain circumstances is a little bit more accurate than just the left endpoint or the right endpoint Riemann sums. Okay, that's all for now.